sometimes we even run out of sandwich.
Oh, okay. All right. So let's get started. It's a pleasure to introduce today's speaker, Carrie Lowe. Carrie is a bsac member in the 2000s era. She got her Ph.D. in 2007, co-advised by Roger Howe and Professor Sujay Kim Liu on the and she did, this is probably the first PhD dissertation on silicon germanium MEMS.
No,
that
was
NGFN was first germanium. Oh, okay, all right. But sort of very promising MEMS technology, low temperature that can be directly integrated with CMOS. And after Carrie got her PhD, she joined Silicon Cloud, one of the first companies trying to commercialize MEMS devices. It's a tiny device based on silicon germanium technology, spearheaded in standing up the process in the foundry. Later, she now joined InvenSense. In between, I guess it's another company, Intermolecular. So she has a lot of experience in industrial application of MEMS or commercialization of MEMS. So it's great to hear her talk about industrial challenges for MEMS manufacture.
Thanks for the introduction. It's an honor to be invited to the bsac seminar. The last time that I did a talk at bsac seminar was back in 2006 when I gave my dissertation talk. So the room is only the fancy camera. So now we live in an era that we witness the MEMS technologies changing the world and changing our everyday life. I think nowadays everyone has a few MEMS sensors in your pocket, in your car, at home, at work, almost everywhere. However, compared to the mainstream CMOS technology, the MEMS technology is still considered a specialized process in the foundry with executing challenges. So I have worked on a few MEMS technologies since I graduated bsac, and I would like to share some of the challenges that I face in my career for bringing the MEMS technology into the foundry. So this is a recap of my information. So I was at bsac 2001 till 2006. My advisors are Professor Howe, Professor Kim Liu. My thesis was on silicon germanium MEMS integration of CMOS electronics. So by the time that I graduated, there was a startup Silicon Clocks, co-founded by Professor Howe and his postdoc Dr. Carrie. The silicon clock was the product that they looked into was trying to use silicon germanium to do MEMS resonator, and the projected market is to replace the quartz crystal for timing reference. So in most of the cases, graduate student research does not get an immediate commercial application. So for me, that was a once in a lifetime opportunity. Then I joined Silicon Clocks right after graduation, continued to work on the MEMS technology, and Silicon Clock was later acquired by Silicon Lab. So in 2015, Silicon Lab decided to get out of the MEMS business. Then I joined Intermolecular, which does ALD and PVD equipment and material study. After 2 years, I decided to come back to the MEMS industry, and I joined another startup, InSense, which was a spin-off from Stanford. This company also tried to do MEMS and CMOS integration, but they switched the material to a specialized copper as the mechanical material. I am now with TDK-InvenSense. InvenSense is using wafer-to-wafer bonding. So that is their way of doing direct integration of MEMS and CMOS. So looking back in my portfolio, I spent lots of time trying to do MEMS and CMOS integration. And all my jobs have bsac connections. So I keep running into friends from the Micro Lab and bsac again and again. So This is a summary slide of the mindset change of working from a lab like micro lab, nano lab, and then a startup, and then going all the way to a major MEMS company working with the leading foundry in the world. So as a student in the micro lab, I think most of your goal is to make it to graduation. So all you need is to have one single working device out of the nano lab. Then you can publish your field paper, get your advisor to be happy to sign off your thesis. And what you're hoping for is that whenever you're working in the lab, the new user that you train like in the morning will not break your favorite equipment before the paper deadline. And then in the case of startup Silicon Clocks, so we started with the goal of going IPO and also with the ambition of changing the world. Since we were funded by the VC, so the VC would like to see the technology being demonstrated with a working device. It doesn't have to be mass production, but they want to see a working device so that they feel secure for their investment. The VC also want to make sure that the product the startup is working on has a potential market, that it can replace some existing technology with better performance and a lower price. And you can also sell millions of those. So with the technology and the market on the table, the next big item is that this startup needs to have a foundry partner who is willing to bring your process into mass production. So that is a big thing for a MEMS startup because MEMS process is still not mainstream. So whenever a foundry signs up for your process, they need to do something new to bring up your process. And in the case of TDK-InvenSense, I think it has similar challenge during its startup phase, but when I joined in 2019, it's already a major player in the MEMS industry. So the goal for InvenSense is to have commercial success. We are shipping millions of parts to customers. We need our product to meet customer spec, and we need to control the cost at the foundry. Also, we need to have consistency in yield and quality for the product. So my job description as a process engineer changes along these 3 stages. So in the micro lab, I spend long hours in the clean room, usually late at night. I did everything myself. And then in the startup case, I went into the clean room once a while. Most of the time, I will prepare instruction so that operators will run the non-critical steps for us. And then when it comes to special tool and critical steps, I will go into the clean room and set up the equipment and the recipes myself. So in the case of InvenSense, we are working with the world's leading foundry. That foundry needs to protect all other customers' privacy or confidential information. So no customer is allowed to enter their clean room. So my job as a foundry engineer at InvenSense is mainly the communication bridge between our internal design team and the foundry partner. Oh yeah.
Could I ask, in the case of silicon clocks, where you're trying to demo the technology, were you guys working in the lab to do that? Or
we started in the nano lab and then we have to move somewhere else because the nano lab, like, we have problem having equipment during the daytime. Yeah, like we couldn't send people to come work at night. We try. So this is a summary slide of silicon clock and the MEMS technology. So in the early 2000, the silicon germanium MEMS research was led by Professor Hao and Professor Sujay King's group here in Berkeley. And then in 2004, grad student Sunil Bahe and a postdoc Emmanuel Carrie under Professor Hao's group, they went to Harvard School of Business and proposed a business plan to use silicon germanium to build MEMS resonator. So there were 2 engineers working together with our business guy, and they make it all the way to get best technology award for UC Berkeley and UCSF. So that was a big thing in the office, and then we put the paycheck under the cloud. So this is the old time of 373 Corey Hall. So that picture was taken downstairs. And in 2006, so Professor Howe and Dr. Carrie continued to work with the VC. So the Silicon Clocks was founded in 2006. So the initial product that we look at is to make MEMS resonator to replace quartz crystal as the timing reference. And then the bigger ambition is that we would like to make silicon germanium a standard process platform in the foundry so that it would be something like a CMOS foundry that other customer can design this process. So the first device was demonstrated within a year of after founding Silicon Clocks. And during the first year, everyone was talking about going IPO. And then it came the financial crisis in 2008. Then the VC starts to be more cautious, and they were looking at an exit strategy. And Silicon Clocks was introduced to Silicon Labs as a potential buyer. And in 2010, Silicon Labs acquired Silicon Clocks. So then we became the Silicon Labs family. So the picture here is the acquisition party in 2010. So that was the full team of Silicon Clock at the end. So in 2013, the CMEMS resonator was announced by Silicon Labs. So at that time, we already had the process transferred to the foundry and got the U up. However, in 2015, Silicon Labs decided to change their strategic direction, and they no longer want to do MEMS business. And that's how the CMEMS technology became history. So the picture in the middle is the farewell party in 2015. So everyone there was on the MEMS team. After Silicon Labs, a few years later, we were invited to document the CMEMS technology in a chapter in Professor Isashi's book, 3D and Circuit Integration of MEMS. And the book got published in 2021. So this is image of how the CMEMS resonator looks like. So we can start with the SEM image in the middle. So this is a top view SEM image. So in the middle, the square in the center is the MEMS resonator, the play resonator. So the light gray color in this image is silicon germanium, and the dark gray color is the oxide. So on the right side, there's a zoom in cross-section image that is making a cut here. So in this image, you can see that we have silicon dioxide being embedded into the silicon germanium structure layer. The purpose of having the oxide slit is for temperature compensation. So silicon germanium will get softer as temperature increases, and that will cause problem when we are doing timing reference. If the temperature is changing and your clock is the clock will get off its target frequency. So the purpose of the oxide is that the oxide will get harder as temperature increase, and then this will compensate for the temperature drip. So around the plate, there are 4 electrodes on 4 sides. Those are the drive sense electrode. Between the electrode and the plate resonator, there's a small gap here. This gap is 0.2 micron. This was not defined by lithography, but instead we use a germanium spacer deposition to define that gap. So the image on the left, so the blue and the gold color here is the same plate resonator, but this was generated by a process simulation software. And then at the bottom, we Photoshop in the CMOS layer, the CMOS metallization, to demonstrate that we are doing the integration directly on a CMOS wafer. And then the marketing team did some fancy stuff in the background to make this an eye-catching poster. This is my one slide demonstration of the CMOS process. So the term CMEMS comes from the contraction of acronym CMOS plus MEMS. This is a 6-mass surface micromachining process. So we are starting, the starting material is a standard 0.13 micron CMOS wafer, and we have aluminum as the top metallization. So the image on the right is a layout image of this resonator. And then the image here is generated by a process simulator that we can do a tilted top view, and then I make a cut, diagonal cut along the center of the plate. And then here I do a zooming cross-section image on the right. So from this cross-section image, you can see that we have the aluminum top metallization from the CMOS wafer. And then we use a silicon germanium via as electrical connection. So this involves a plug layer and then later an electrode layer. So there were two depositions here. And then the slightly brighter color is the structural layer of silicon germanium. So we make a connection to the plug, the electrode, and then to the structure. On the right side, that is the proof mass. The proof mass also has a similar electrical connection to the aluminum top metal. And then embedded in the silicon germanium structure, we have this oxide for temperature compensation. So the reason that we use silicon germanium as the structural material because this can be deposited at CMOS compatible process temperature. So whenever we do a deposition, the CMOS underneath will not be damaged. And also polysilicon germanium has very similar mechanical properties as polysilicon, which is good for the quality factor. Between the proof mass and the electrode, we define a 0.2 micron transducer gap using the spacer deposition. And underneath the structure, we use germanium as the sacrificial layer. So during the release process, we put the wafer into heated peroxide solution. Then the germanium spacer and the germanium sacrificial will be removed and the structure can be released. Yeah.
Can I ask, I guess, what temperature you were able to go?
So this one we do 410.
410.
Yeah, but there's still room to go down, but then you have to trade off some mechanical properties and depth rate and things like that.
We still use that for the MEMS for the relays.
So this is an image to demonstrate the encapsulation process. So after we finish with the CMOS wafer building the MEMS on the top, so like this, we call it the device wafer with the CMOS and the MEMS. And then on the CMOS wafer, we have aluminum top metallization. So that aluminum has two purposes. So we'll open it up so that we will do a sealing to bond to the cap wafer. And then also the aluminum will be opened up as the wire bonding pad. The process for the cap wafer is very straightforward. We first do a deep etch into the silicon, and then we generate that cavity. And then we do a titanium deposition. So the titanium is serving as the getter material to absorb outgassing. And then on the sealing, we do oxide deposition as electrical isolation. And then the germanium is deposited. So the germanium will be eutectically bonded to the aluminum. And we create a hermetic seal for the resonator. So after bonding, the wafer will continue with grinding, so it gets thinner. And then we do a half dicing so that the cap wafer will be diced off and we can expose the aluminum pad. So the image on the upper right is the SCM image of the eutectic bonding. And then the image on the lower right is a top view of the wafer where you see the cap and then also the exposed aluminum bond pad. So this wafer is ready to move on to wafer level electrical testing.
What's the bonding temperature?
It's also CMOS compatible, but I don't remember it on top of my head. So the MEMS process development. So as I mentioned, we started the initial research in the micro lab, and then we tried to send engineer here to build the process. But since the lab was very crowded and we couldn't have enough daytime equipment reservation, so then the VC was bugging us that they want to see a working device. That's how we decided to move to SVTC, Silicon Valley Technology Center. Fab, SVTC, is serving like a stepping stone between the lab to the big foundry. So they have 24/7 operation. So for us, it was a lot easier because we could set up run cards for the operators to run the non-critical steps. And once it comes to the critical equipment and critical steps, our engineer will go into the clean room and set them up. That was a tool that we use heavily in SVTC, which is a wafer level SEM inspection tool. So it was really helpful, like when we were developing an etch process. So once the wafer gets out of the etcher, we load it into the wafer level SEM tool for an inspection to ensure the etch is inputted correctly and all the material is removed. If not, we'll just go back to the etcher to add some over etch. And we also use that SEM tool to take lots of pictures, preparing documents for the fab transfer. So the last stage was process bring up at SMIC. So after we were acquired by Silicon Labs, SMIC was our foundry partner. So when we started at SMIC, we started with a huge stack of documentation showing the step-by-step process description with lots of cross-section images. And at that time, SMIC was fairly new to MEMS process. So they welcome our engineers to go into their clean room and work side by side with the engineer. So there were 3 of us that took turns to stay in SMIC for about 3 years. And at the end, we were able to achieve about 95% yield. So in terms of the challenge for the MEMS process, most of the process steps and equipment, they were standard as SMIC, and with the silicon germanium process as the exception. So for the business discussion, it was not easy for a startup to go against a big foundry because we need them to spend capital expense to set up a furnace and set up a process flow for us. So on SMIC side, they were considering having the resonator would be a good business after mass production. And then we showed them the bigger picture that so SMIC could become a MEMS foundry with the silicon germanium process, enabling them to have a design house in the future as their customers. So other people can also design in the same process. So in terms of the technical discussion, the silicon germanium process was always under the spotlight. It was heavily discussed for manufacturability, throughput, and cost analysis. So, so this is a slide summary of showing how we bought the silicon germanium process from the micro lab all the way to SMIC. I have worked on 3 different generations of silicon germanium furnace. So for those of you who are still working on silicon germanium, you must have seen this image in the TISA 20 manual. So this was a horizontal furnace in the micro lab, and it's an R&D furnace. So on my thesis, half of it is on materials property study for silicon germanium, and then the other half of it was on modifying this furnace to make it more repeatable and more maintenance friendly. So I was working closely with a few micro lab staff, Bob Hamilton, Jimmy Chen, modifying the furnace for a few years. And the second generation of silicon germanium furnace was built at SVTC. The furnace was made by Avisa Technology. So we were focusing on making it repeatable and improving the uniformity. And then we learned lots of big lessons on particle control. So particle was never a problem in the micro lab. Well, it's like nobody cares. You have particle on a wafer, you just use the air gun to blow it off. But at SVTC, if they see particles on our wafer, the wafers will go to quarantine. They cannot move on to the next step. The third generation of the furnace was built as it was made by Hitachi KE. So this is the vertical furnace that is shown on the right. With this vertical furnace, we focus on the throughput, uniformity, and then we do a lot on the SPC control and also make it maintenance friendly. I think for the interest of time, I cannot go into the details of how the third generation is much better than the first generation, but all the information are published in Professor Isashi's book. So this is the last slide. So why didn't the CMEMS technology mature to the market? So in my perspective, so we got the yield going up to 95% in SMIC, but then late in the stage when we announced the CMEMS translator, we discovered some design issue pretty late. And then at the same time, the quartz crystal process was improved and it got cheaper. So therefore, the projected MEMS residential market got smaller. And Silicon Lab was a little concerned about that. And then at the same time, there were those big things like IoT. So then they decided to get out of the MEMS business and move on with the IoT. So there were a few mistakes made along the way. So we wasted about a year to move the SMIC process from its Chengdu fab to Shanghai fab because of the SMIC reorganization. And also the MEMS team was distracted to work on inertial sensors for some time. So that's why we didn't catch the design issue early enough to fix it. So when Silicon Labs decided to change direction to get out of MEMS, some VCs and SMIC was actually interested in funding the CMEM technology as a late stage startup. But Silicon Labs was stubborn. They want to keep all the CMEMS related patents, but they don't want to work on it. But a few years later, after everyone lost interest, then Silicon Labs sold all the patents to SMIC. Okay, now switching gear to talk about TDK-InvenSense. So initially it was InvenSense, not TDK-InvenSense. So it was a startup founded in 2003. One of the bsac alumni, Joe Seeger, was one of the co-founder. It made it to IPO in 2011. So in 8 years, that's very good. And then it was acquired by TDK in 2016, and now we are called TDK-InvenSense. So TDK-InvenSense is a very successful model for MEMS design house with outsourced fabrication. So we do not have a fab, we do not have a clean room. We all the fabrication is outsourced. So InvenSense started with motion sensor, starting with a gyroscope in particular. The initial market was to make MEMS gyroscopes for the high-end camera industry so that they can stabilize the image. And then later, accelerometer was also added. And with the cell phone market, the consumer industry, like the consumer market for MEMS sensor got expanded significantly. And then InvenSense expanded all the into other MEMS sensor area, including ultrasonic time-of-flight sensor, microphone, and pressure sensor. So next week, we'll have Richard coming over to talk about the ultrasonic time-of-flight sensor. So my slide later will mainly focus on the work that I do in motion sensor. One of the core pattern for InvenSense was the nice series fabrication process. So this is the process that we use for motion sensor. What it does is it's use wafer-to-wafer bonding so that we can do direct integration of MEMS to CMOS. So in the image here, you actually see 3 different wafers. So the top color, the blue one, is the silicon cap wafer. And then in the middle, the yellow color, including the red, is the core MEMS wafer. That's where we define the structure for accelerometer and gyroscope. And then the gray color wafer at the bottom is the CMOS wafer with all the circuit. So this process is very cost effective and is compatible with high volume foundries. All the process steps use commercially available equipment, and all the processes are standard off the shelf. So on the structure layer is using single crystal silicon. That is very nice for the designer to work with compared to polysilicon, because single crystal silicon has better material property than polycrystalline silicon. And then at the end, we do a wafer level bonding, eutectic bonding for the MEMS wafer to the CMOS wafer. So this creates a hermetic seal. And then we also have an electrical connection between the CMOS and the MEMS. So I'm going to break down the Neisseria process wafer to wafer. So starting with the cap wafer. So this is very straightforward. You just etch a cavity into the cap wafer, and that defines your inertial sensor's cavity volume. And then the next step, so we do fusion bonding of single crystal silicon wafer onto the silicon cap wafer. So this is fusion bonded. And then after bonding, we polish the silicon structure wafer down to the target thickness. So it's grinding and polishing and CMP. And after that, we do lithography to define the standoff structure. So this is the standoff layer that will be bonded to the CMOS wafer later. And the last lithography is to define the actuator, the accelerometer gyroscope on the structural material. The last wafer in the process flow is the CMOS wafer. We use a standard CMOS wafer, and then we do minor modification in the last few process steps of the top metallization and the passivation. So at the end, we do eutectic bonding of the MEMS wafer on the CMOS wafer. So that is a layer of germanium on the MEMS wafer that is being bonded to the aluminum top metallization of the CMOS wafer. So this eutectic bonding will give us a hermetic seal, and we also create electrical connection. So since TDK-InvenSense doesn't have a fab, so what the foundry team does is to manage the relationship with the foundry. So TDK and our foundry partner, we are working as a team, but at the same time, we also need to respect each other's technology secrets. So as I mentioned before, customers are not allowed to enter the clean room. And also the foundry partner, they also have a very strict policy on their own engineer. So their engineers are not allowed to bring the cell phone into the building. So whenever they go to work, they need to check in their cell phone at the front desk and then trade for an old-fashioned phone that doesn't have a camera, and it only has the basic function of making a phone call. So since we tape out to the foundry, so the foundry will have access to our layout, but we will not disclose any design details. So in terms of some of TDK's secret, that includes the design details, the MEMS design rules are owned by us. And then we also have our own process simulation model that is not being shared to the foundry. So on the foundry end, they will not disclose their process integration details to us. The equipment that they use, the material that they use, those are also confidential, as well as the process recipe. So we sometimes just know there's a process A versus process B, but we don't know what it contains inside the recipe. So in terms of collaboration, we work together on the design rule that is process related. Anything that's design related will not cause a problem in fabrication. Those are called the design related rules, and those are not disclosed to the foundry partner. We also work on process and design risk assessment together, and we do manufacturability review before we launch a new product. So part of the foundry team's responsibility is to help with launching a new product. So since the market is changing, so we need to come up with better technology and new products once a while. So the foundry team will lead a discussion of a risk dashboard. So we'll list down all the design requirement by the projected market. And then we'll write down the risk item that is process related. We'll come up with the root cause, hypothesis table, and a mitigation plan. The other important part is that we need to come up with a timeline for the development and make sure that it's within the projected market window. So once TDK and the foundry partner agree with the risk dashboard, and we can proceed with the tape out. So the design team will do design splits, and then the process team will lead process split to work with the foundry. So in the process split, we'll run the target condition, which is called the POR condition. And then we also need to run corner cases, which is considered as the natural variation in the fab. So we want to make sure that the product can meet the customer spec with the process variation that we naturally see in the fab. So once the wafers are fab out, we'll continue with testing and validation. Sometimes debug will be required. Then we'll have a down selection on the design if everything goes well. Then we can proceed with product tape out and ship parts to customers. The other job for the foundry team is to work on technology development. So we need to come up with new technology continuously so that we can lower the manufacturing cost, have better performance in the product, and also improve the quality. So whenever we try to launch a new process development project, we need to have a few requirements. The first one is that since TDK-InvenSense is not a research institute, whatever new technology development we do, we need to have a target product for interception in mind. So if you don't develop a technology for a product that is pure research and it's not going to make money for the company. Also, for any process-related technology development, it's usually a collaboration between TDK and the foundry partner. So if the new technology is introduced by TDK but not the foundry, so we usually end up with just filing a patent. But if there's something is introduced by the foundry but not TDK, we will not do electrical validation support. So only in the case that when the new technology is introduced by both parties, and we'll work together to make it happen. So all the new technology development will have to go through manufacturability analysis, ensure that we have sufficient process window, process equipment capability, and also the cost makes sense for the new product. Also, any new process module is supposed to be qualified on existing product where the design is proven. So if something is not going right, we know it's the process that needs to be modified, not the design. The other thing that I do as a foundry engineer is to run simulation for process predictability. So since I don't go to the clean room anymore, so that's my new way of doing process engineering. So that is always a discrepancy between the design and the manufactured device. So I'm using the deep RE edge as an example. So this is a critical step in our process flow because it defines the actuator layer. The deep RE edge is known to have a pattern dependency. So as shown in this SCM image, when you have a small gap, your edge is slower compared to when you have a big gap. So, so in our case, our accelerometer and the gyro, they have different gap size along the entire device. So what the designer usually wish to have is that they were hoping that they get a straight sidewall for all the gaps that they draw in the layout. But in reality, once the wafer get out of the fab, we get all kinds of different sidewall profile based on the gap size. So I work on building a process simulation model so that we can predict the device geometry at the time of tape out before we run the wafers in the foundry. So the input of the process simulation includes the layout, and then we also put in some cross-section image for the model calibration. And with that software, we are able to output some virtual metrology so that we can predict the actual edge profile that we will get in the fab. So this slide is on failure analysis. So we usually catch failures by electrical test. So we have to run the wafers through electrical test. Every device will be tested. If we see a wafer pattern on a particular parameter, so we'll trace all the wafers with a similar parameter, and then we come up with a hypothesis table on what could go wrong. And then the foundry team will contact the foundry to look up some SPC data, which includes inline and offline measurement as the process control monitor. Then we do a correlation study with the process parameter. And also with all the wafers with a similar pattern, we'll also do a tool commonality check. If we find out all the wafers went through a particular tool and have the similar pattern, and then the foundry will take a closer look at that tool and see what could have happened to it. So at the end, once we finish the debug phase, we'll put together a lesson learned document which describes the problem. We'll put down the root cause analysis, and then we'll list down the preventative action, which could possibly including modifying the process in the foundry, making design change, or coming up with a new design rule to enforce a certain geometry. So back to the lab to fab slide. So looking back in my career, so when coming from the micro lab to a startup and to working with a major foundry. So in the micro lab, nano lab stage, with the goal of graduation, you are supposed to work long hours in the lab. You need to have some good luck. You have to hope that the equipment is working the way that you want it. And of course, you want to have some fun whenever it's possible. If the equipment goes down, you need to go out and play some video game. So in the startup case, with the goal of going IPO and the ambition of changing the world, you have to keep in mind that you need to look into when your product can get into the market. So statistically, only 1 out of 10 of the startup can make it to IPO, and even less than 1/10 of that will be able to change the world. For the case of a major MEMS company with the goal of commercial success, we need to be sensitive to the new market requirement, and also we need to keep doing technology development to keep us competitive. So as you can see, all these 3 stages will require hard work and dedication. Right. So right in time.
Thank you very much. We know how much effort and care must be spent by a great team of people to get an idea into something like our cell phone or watch. So questions?
Yeah.
All right. Thank you. That was an awesome talk. It's great to hear all of this in one place. So my question is that it sounds like it takes a huge amount of work to develop a new MEMS device.
Yeah.
What would you say is the minimum required to commercialize something successfully? Like, what is the minimum market size and
actually, that is a business question that I'm not very familiar with. So like we usually have, so when you have a startup, you don't start with only engineers. You need to have a business guy in your team to analyze the market and to see how many products that you can project for the new market and how much margin you need to make it profitable and make it to IPO.
All right. Do you have any rough guesses, maybe not of money, but of like, would it be feasible to make a single one-off device for a single customer?
That is also market for that, because there are certain, so for MEMS, there are certain things that it might not need to, you don't need to have millions of parts, but there's some small amount of parts that customers are willing to buy. But then you need to do a trade-off on how much does it cost you to make that device and how much the customer is willing to pay. Yeah, I think that like during my time in the microlab, there were quite a few startups making like a few devices to sell to customers. They are profitable, but they do not scale up.
Okay, so you would only see that at like the micro or nano lab and not at medium or large.
I think like even in the medium lab, there are also people making small batch of products.
Any other question?
Yeah.
Who was the nano lab director while you were trying to get your stuff done in nano lab?
Few founders.
Was the director? Was that me?
Probably not. Well, I think is it a lot easier to get access to the
I
equipment?
just wanted to.
I'm not responsible. I can't take credit.
Nano lab, I think it was.
Oh, it's been Bill founders. Like it was Catherine and Vogels and then Bill founders.
No, the bill is the that man is a faculty director. I think that
Maybe it's Sujie at that time.
Yeah.
When you look back at your career thus far, working at the early stage startup, the acquired, trying to get the product out, and now the big company, what part do you look back like most fondly of, or like for the most exciting time? I think
That would be the
the
Silicon Cox. It's like my baby. So I would say starting from the beginning to the end with no regret.
Would you do it again though?
Sure.
I was hoping you'd say the micro lab.
No, the microlab has lots of frustration.
So more serious questions. If you put all this blood, sweat, and tears into this silicon germanium CMOS process, and that went to SMIC. Is that still at SMIC?
They have all the patents, but like I actually approached them once after they acquire all the patents and asked, do you want to bring that up? I can help you. But then there was lots of business model change, and then that didn't happen. But they still have all the patents, and they can rebuild the tool. This customer, they have all the blueprint and the drawing.
Start up the process.
Yeah. Yes.
Are there questions from online? So I have a question. So knowing you're going through these three phases and you're seeing, the last process, a series process you described, sort of is a simple and fast to market using all available equipment. You don't need to invent anything. But looking back, there's still a lot of many beautiful details you can do with silicon germanium, these new materials. Would you do it again, pursuing this kind of new material, new process?
Yeah, that's possible. But like silicon germanium is not suitable to make inertial sensor comparing to the 9 series process. It's nowhere cost compatible. Yeah.
If you could somehow change how foundries or MEMS device development worked, what would you change?
Actually, that is a big question. I think it's never easy for a MEMS startup because like you have to have someone who's willing to work with your process, and that involves lots of capital expense. So it's like you need to start with lots of money, and that is not an easy thing. And the VC will not give you all the money to build your own fab.
Great. Let's thank Carrie again.